So thank you for a really nice introduction. Good afternoon, everyone. My name is Emma Kukuljan and I'm coming from University of Rijeka, as Professor said. So I'm really happy I get the chance to share this with you today because this actually was my master thesis I just recently graduated with. So what I did for it was development of a numerical model for estimating the hardness of steel after quenching. General introduction. We all know quenching to be a process to enhance hardness or other mechanical properties, usually of a steel one. And to achieve the desired hardness distribution, we have to properly define and optimize the quenching parameters. This can be quite time-consuming and even maybe expensive process. So modernly, we introduce a numerical simulation to help us facilitate and accelerate this task. So for this project, I developed a transient thermal numerical model that enables the simulation of quenching process. So just a general setup that we did here, we used ANSYS Mechanical, so the finite element method was used. I developed a parametric APDL code that is able to adjust for different sizes of geometries and different steel properties. So as we are simulating the quenching here, this is by all means the thermal transient analysis. And we modeled the axisymmetric model because we assumed the metal sample to be a cylindrical one. So we did an approximation of this, and we also assumed the symmetry. So we only focused on modeling this part of the sample to accelerate the analysis time. So the general idea here was to develop a numerical model whose output is cooling curves for each of the nodes. So those cooling curves give us a specific information, and that is the cooling time from 800 degrees Celsius to 500 degrees Celsius, which is crucial to later determining the hardness using different geometry diagrams. So before we even started creating this model, we needed to have some kind of reference guide to verify development of our model. So we used the reference cooling curves from literature. Here are the information of cooling of both core and surface for steel 34 chrome 4. Here is information about 3 different dimensions of samples. So there is diameter 95, 48, and 28. And for this project, we only focused on quenching in oil. So we started modeling, trying to describe the same situation we had with the reference curves. So as I mentioned, the analysis type is transient thermal analysis. The model was approximated to axisymmetric model. And material properties are the ones according to the reference steel information we have, that is 34 chrome 4. So we imported all the properties into our code. Those are thermal conductivity coefficient, density, and specific heat. All of these parameters are a part of Fourier's law for heat conduction. For dimensions, we simultaneously compared 3 different sample sizes, so diameter 95, 48, and 28. The meshing was dependent on convergence for each of these sizes models. Initial condition was defined as 800 degrees Celsius in every node. And now we come to defining the load. So as this is a thermal analysis, the load here is actually convection on exposed borders. And since we're modeling only this part of the sample, the convention is applied to the red borders. And convention is described by heat transfer coefficient. And here we come to the realization we have two crucial parameters that are still undefined at this point. And those are both thermal conductivity coefficient and heat transfer coefficient. So this is coming to be the more complex part of this project, because both of these coefficients are crucial and root of development of quenching simulation, but both of them are temperature dependent, and they vary a lot depending on temperature rises and downs. And as we know, quenching, we have a lot of temperature fluctuations. So both of these coefficients, we don't know the distribution of, because they are dependent on a lot of quenching parameters. So what was needed to be done for this situation is we needed to simultaneously perform iterative calibration of both of these coefficients, trying to use some kind of previous research, which was really limited. And by the end, we got some final results. Here is it shown. So these are the cooling curves we have for our set steel. This is only for the smallest sample dimension. So this is for diameter 28. We have reference curves for core and surface, and we have what we've got. This is the same for a bit bigger sample. So this is for diameter 48. And this is for diameter 95. And here is an overview of all of them. So we can see quite a deviation in the initial time of cooling. But what's crucial for our project here is actually determining, as I said in the beginning, a cooling time from 800 to 500 degrees. So that's what in our method determines the hardness later. So we only focused on trying to align these curves and this specific area as much as we could. And we agreed that this was good. But the story doesn't stop here, because still we are not, even the curves align. We are not sure if our model actually is able to predict the hardness properly. So here we introduce the reference sample, for which we have experimentally determined hardness in 9 nodes. These are the sample information, so it's different still, but still similar. And we adjusted our APDL code according to this information to now simulate this situation. And here are the results. Here are the 9 nodes we have the experimental hardness for. And what we are now doing is getting the cooling curves for each of these nodes, determining time of cooling from 800 degrees to 500 degrees Celsius, then going to the transformational diagram just so we can get Jomini distance with which we can later determine the hardness. So that's exactly what we did for all of the 9 nodes. And here is our results. And here is the results compared to the experimentally determined hardness. So you can see that in each node, the deviation is less than 10%. And the biggest deviation we have is in node 7. It is 3.5 HRC, which is still assumed to be quite good. So with this, we concluded that this numerical model is properly defined for assuming the hardness distribution after quenching. So quick debrief of this all, I developed a numerical model to predict the hardness distribution of quenched steel in oil. So we've got cooling curves from this numerical model, which we calibrated using literature. And then we estimated hardness based on cooling time from 800 to 500 degrees in geometry diagrams. So we are satisfied with the results, and some outlook for future work would be to adjust the code to be able to simulate even maybe more complex geometries or bigger variety of materials. So that would be all from me. Thank you all for your attention.